So today we are talking about implicit differentiation. It sounds crazy. Let me show you what we need this for. We'll go out to Desmos. Up to this point, we have all the functions that we've looked at, and we have looked at some crazy ones, but all the functions that we've looked at have been functions in terms of x. What do I mean by functions in terms of x? Well, that means I have y equals something, some function of x. It could be x squared, like I've drawn. It could be sine of x. It could be sine of e to the x, right? We've done those type of ones. But all that we've done, and we, like I've said, have said, oh, we're frozen. So, unfreeze. There we go. There's our sine e to the x. Okay? So all of these have been a y equals or f of x equals something of x. Okay? It's always been in terms of x. Today, we are going to expand our minds and expand ourselves. And what if I had something like this? X equals like sine of y. Can I do that? Yes. It's not a function of x, it's a function of y. It's not that crazy. But what if instead I had something like this? X squared plus y squared equaled 16. That's a circle, right? Can we take the derivative of that equation? Yes. Because do we have tangent lines happening there? Yes. Like if I'm right up here at the top, what would be the slope of my tangent line? 0. So we can still do these. But we cannot do it with just what we've known. We need to know implicit differentiation. Let's go a little bit crazier. Let's say, what if I took this and had, let's add a 2x there. It's not a function of x. Most definitely it fails the vertical line test. But it's still an equation. It's still a curve. And all our properties of derivatives still apply. What if I did this? Let me just change my power. Why? I'm just showing some of the crazy kind of graphs we can have. That's a fun looking graph. What if I did this? I added in a 4x cubed y and hit minus. Look at that thing. Oh my God. That looks cool. It does kind of look like a foot, right? But we could differentiate that because, hey, right here, wouldn't that be a horizontal slope? Wouldn't I have a vertical slope here? All of these places have slopes. We can do our derivative. That one was a mistake second period, but I thought it was kind of cool, so I'd show you. The one I actually meant to do was this one. Look at that. You remember the flower from last year? Let's see, what was the flower? That was our polar curves. So, polar curves is actually a BC topic, but those can have the derivatives. Be something, let's see, what was our polar curves? Let's see if I remember. What was that? R equals like 2 cosine of like 3 theta? Yeah, there we go. There's one. Something like that, right? So we did polar last year. This is not implicit differentiation. This would be polar differentiation, which is a BC topic. So we won't see that this year, but those of you going on to BC, we will see these again next year. Okay? So we can do that. But so today we're going to be looking at those ones where it's not just a function in terms of x, it's other things, some cool things that can happen. Some cool looking curves. So, let's get into the math. Let's start with this one. Can we find the derivative of this with what we know right now? It's actually a yes. Why? Because can I get this so that it is a y equals a function of x? How would I do that? How would I isolate my y? I can maybe add the y over, right? Or subtract the 2x, however you decide to do it. And then I would have y equals, what would it be, 2x squared minus 5? So if we're able to get it in terms of x, go ahead and do that. Isolate your y. Because now I can just take the derivative. What's y prime? Just 4x. And we're done, right? Nice and simple. The problem comes into play when we have something like this. And our question is, can I do the same thing? Can I isolate my y? You might be able to. I don't even know where I'd start, to be honest. I don't know where I'd start isolating my y here. Because I have a y cubed, a y squared, and a 5y. I don't know. So I can't do that. This one needs implicit differentiation. So we can say can't isolate y. Needs implicit differentiation. So we're going to explore a couple things and then actually go through our implicit differentiation steps. So let us start with something simple. What is d dx of 3x squared? That's just asking our derivative. So our derivative is 6x. We know that, right? What we haven't realized is that this d dx actually does have some importance here. What variable did we take the derivative of? So actually what happens, we haven't done it because it doesn't really change anything, but what happens there is that this is actually a dx dx. So this right here becomes dx over dx. It's the derivative of x with respect to x. But then what is dx divided by dx? So that's why we didn't need it, because that goes down to 1. Okay? Why do I mention it? Because, exactly, because we will have something like this. What is the derivative of 2y cubed? It's just the power rule, right? What is it? 6y squared. But now, thinking about what we just talked about, what would I have next to it? dy over dx. Because I took the derivative of y with respect to x. That's how it's worded. Can dy dx cancel out to 1? No. It cannot. Okay? So we leave it. That's our dy dx. And actually, if we think about it, going back up to something like this, where I had y equals 2x squared minus 5, what if I said, hey, what is d dx of that? What would we do? Well, in implicit differentiation, we don't just say y is y prime. It is. But what is the derivative of y? 1 dy over dx equals 4x. That's where this dy dx comes from. And that's why we're able to say y prime is dy dx. because we have the derivative of y with respect to x. Let's go down to this one. So what would be the derivative of this? We have x plus 3y. Start it out. What's the derivative of x? 1. And I'm going to just write dx over dx for right now. Do we really need it? No, because it's equal to 1, but we're doing it to be able to see what's going on. So 1 dx over dx plus, what's the derivative of 3y? 3 times over dx. But since that cancels out to 1, it's just 1 plus 3 dy dx. Please do not say that that's 4 dy dx. It is not. I had somebody earlier today, they tried to take the derivative and said, hey, that is 1 plus 3 equals 4 dy dx. That is wrong. Don't do it. If I look down here, 1 does not have a dy dx. It's not a like term. I can't combine it. Okay? I want you to think about d. What would we do with d? D dx of x times y squared. Think about it. Talk in your groups. All right, everybody. Let's talk about d. First off, what rule do we need? Product rule. Same product rule we've been using. So, why? Because I have an x times y squared. That's my u and that's my v. So let's think about that. What is the product rule in terms of u and v? U times plus vu prime. Yeah. So let's do this. What would be my derivative? What's u? X v prime. 2y. But I took the derivative of y, so what do I need? dy over dx. Whenever we take the derivative of y, we have to have dy dx. Always. Plus, what's v? Times, what's u prime? 1. Technically the dx over dx, right? But what is dx over dx? So it goes away. So that would simplify to 2xy dy over dx plus just y squared. Okay? So again, whenever we take the derivative of y, we have to have a dy over dx. Okay? And as we can see here, all the rules that we have learned can still be used. Here we needed the product rule. There might be a time we need the quotient rule. There might be a time we need the chain rule. We've been using the power rule. There might be a time that we have e's and natural logs and sines and cosines, and all the stuff that we've seen can be still used. But this time it's not just going to have x. There could be an x and y. Okay, guys? So, let's look at our guidelines, look at our rules. Like everything, the more we practice, the more we'll come to understand and be okay with it. So, implicit differentiation, step 1. We are going to differentiate both sides with respect to x. What does that mean? That means I'm going to have a d dx of whatever my curve is, whatever my equation is. D dx. Step 2. Any terms that have a dy dx, we want them on the same side. Everything that doesn't, move it over to the other side. Step 3, factor out any dy dx's. And step 4, solve for dy dx using division. Now, reading out those steps, probably are like, I have no idea what that's talking about. That's fine. Let's practice on this problem. Hey, that's the problem we had up in problem 1. This is problem 1b. I said we couldn't do it yet. Now we can. So, let's do it. Step 1, differentiate both sides with respect to x. Please write this as d dx of, and then write your curve, y cubed plus y squared minus 5y minus x squared equals negative 4. Take the derivative of each term. Go ahead and do that. What would be the derivative of each term? Remember, if you have a y, you need a dy dx. Go ahead and do each term. We'll check in. Okay. Sophia, what did you get for the derivative? What's the derivative of y cubed? 3y squared. But I did y, so what do I need with it? dy over dx. Good. Okay. Xavier, what would be the next term? Y squared, what's its derivative? Times dy dx. Next term, Delilah, negative 5y, what's its derivative? Negative 5y, what's the derivative? It's like negative 5x, what's the derivative? Just the 5. But it has a y, so what does it need with it? There we go. That's it. That's it, guys. Now we're on to the x's. Minus x squared, what's its derivative? Technically a dx over dx if we wanted to write it, but that would cancel out to 1. Equals, and then on the other side, what's the derivative of negative 4? There we go. That's it. That's it, guys. We're not done, obviously, but that's the derivative. Okay? That's the differentiation. Let's see, that's step 1. Step 2, what does step 2 say?
Get it on either side.
All right. So my dy dx's are already here, so what needs to move to the other side? So let's add that over. So I have 3y squared dy dx plus 2y dy dx minus 5 dy dx equals 2x. Okay, that's step 2. What is step 3? Factor out. All right, can I take a dy dx out of all of those terms? Let's do it. So dy dx, what would I have remaining if I factor all that out? 3y squared plus minus all that equals. All right, we're almost done. What is our last step? Using division. Why? Because, let's see, do orange. What operation is happening right here where my orange arrow is pointing? So, guess what? I want dy dx by itself. Well, divide by all of this on both sides. And we have our answer. Dy dx, the derivative, is 2x divided by 3y squared plus 2y minus 5. So again, whenever we're taking the derivative of y, what must we have? Whenever I take the derivative of a term with y, what must we always have? Dy over dx, yes. In some, it's the derivative of y with respect to x. That's what it is. You took the derivative of y with respect to x. Why am I saying that? Because in Unit 4, our next unit, we're going to have something called related rates. In related rates, we are going to be taking the derivative with respect to time. So it's going to be d dt. But we might still have something like this, but instead of d dx, it will be d dt. And then I'd have a dy dt, dy dt, dy dt, and a dx dt. Okay? So, we'll talk about those more in Unit 4. But that is why that is there. Let's look at B. I want you to think about B real quick. Talk in your groups. What might we need to do with B? All right. For the several groups out there, say it. What rule are we using? Okay, let's use it. What is my outside function? Okay. What's the derivative of e to a power? What is it? E to its power. Do I take the derivative of that power inside there? Meaning, is this the same as what it was originally? Yes, that's what I'm talking about. Meaning, I haven't done the derivative yet, so do I need a dy dx inside the power? No. However, chain rule, what do I multiply it by? The derivative of the inside. Remember, d dx of e to the u is e to the u times u prime. That's our chain rule. So, looking at the inside, what is the derivative of x? 1. Dx over dx. Plus, what's the derivative of y squared? There we go. That's the inside. That's my e to the u prime. Let's go on to the other side of the equal sign. What is the derivative of x squared? 2x, technically a dx over dx. Okay, that's our derivative with respect to x. However, I need to get that dy dx by itself. So, thoughts? How do we do that? How would I get dy dx by itself? Okay, so I hear a lot of people saying, maybe we can divide by that e to the x plus y squared. Yeah, totally could. But I want us to think about that. Let's just think ahead. So I divide by this. I'm going to have a fraction, right? 2x over that. Then I'm going to have to minus 1 and divide again. So then I'm going to have like a fraction, and it looks nasty, and it will not be any answer on a textbook or multiple choice. What I would recommend when you have a situation like this, no, we have to isolate the dy dx, distribute this in, okay? It's not crazy. What is e to the x plus y squared times 1? E to the x plus y squared plus, just write that as 2y e to the x plus y squared dy dx. We're just multiplying it in. Now, can I isolate it a little bit easier? What do I need to do? Subtract that e, the first e. So minus the e to the x plus y squared on both sides. That will leave me 2y e to the x plus y squared dy dx equals 2x minus e to the x plus y squared. And then we're almost done. We have one last thing to do. Do I need to factor that dy dx out? I know that's a step, but I don't really need it because I don't have more than one term. It's just the one term, so I can go to the last step. What's my last step? Divide it out. What am I going to divide by? All of this stuff that I'm multiplying here, right? So I'm going to divide by 2y e to the x plus y squared on both sides. So our answer, dy dx, that is gone on that side, dy dx equals 2x minus e to the x plus y squared over 2y e to the x plus y squared. Now, that is it. Do not try to simplify that. It can't. Please do not cancel these e's out. Do not cancel out the 2's. Why can we not? Because of the subtraction. If it was the 2x times this, then sure, you'd be left with just x over y. But it's not. It is subtraction. Please do not cancel things out. Terms cannot be canceled by factors. All right, turn the page. Try problem 3, please. I'll give you a little bit more time to try it out, but I want to discuss what is happening on that second term that I just wrote. What rule do we have to use here? Product. How do we separate it? That's our u dot times v. I would recommend, think of that as 3x times y. So that would be your u, that would be your v when you do it. If it was, it's not here, but say it was a negative, like a minus there, well, what I would do is put that negative with the first one, and then that be your u, okay, if it was a subtraction. It's not, it's just an addition, but that is how I would split it. That as your u, this is your v. Okay? The other stuff, all the other terms, just do normally. But go ahead and try it out, please. Take another minute, and then we'll check in. Let's check in, guys. Let's just go through each term. So, y cubed, that one should have been easy. What's the derivative of y cubed? 3y squared? But I'm missing something. Anytime I take a derivative of y, it has to have a dy dx. Let's do that product rule. uv prime plus vu prime. What's my u? 3x. V prime, that's y. What's the derivative of y, ladies and gentlemen? What's the derivative of y? 1 dy dx, right? 1 dy dx. Plus, what's my v? Y times, what's my u prime? 3 times, technically a dx over dx. Do we need to write it, guys? I think we're fine, okay? Minus, and now we're on to the x cubed. What's the derivative of x cubed? 3x squared dx over dx equals 0. All right. That is our derivative. That's a differentiation. You need to isolate the dy dx's. Try it. Try isolating, getting the dy dx by itself. So we need to isolate our dy dx. That's those two terms. So that means these two terms need to go on that side. So we will have a 3y squared dy dx plus 3x dy dx equals, I have a positive 3x squared minus 3y on that side. Okay? Factor out our dy dx, and we have 3y squared plus 3x squared minus 3y. Which y, Rocky? This one? From here. That was part of my product rule. That was my vu prime. Because on that vu prime, my u was 3x. I was taking the derivative of 3x. So it didn't need a dy dx. It was a dx over dx, technically. Okay? So that one doesn't have a dy dx. It needs to go to the other side. Okay? All right. Okay, going on. Then last, divide and we get our answer. So dy dx is going to be 3x squared minus 3y over 3y squared plus 3x. Only thing I want to address on this one is that it can be simplified a little bit. What number do we see on every term? So I could factor a 3 out of the top and factor out a 3 on the bottom. Then what happens to those 3's? So then technically I could write it without the 3's. It would be, this would be the answer in like the book or multiple choice. If it was a free response open, no. That's again all the time, unless I specifically say to simplify, you don't need to, unless you're matching to a multiple choice answer to the answer in the book. Yes. Okay. All right. Any questions? Okay, like I mentioned back when we were looking at the graphs, since we can do our derivative, we can do tangent lines. We can do slopes of tangent lines. Because what is the slope of a tangent line? And isn't that what we just have right here is our derivative? So if I was asked to do the derivative, what would I need to plug in? Like to this one right here. What would I need? The point, the whole point, right? Because if I was just told, hey, derivative at x equals 2, they're like, okay, x equals 2, but what do I put for my y? So you need both, x and y. And if they tell you just x, then you have to go back to the original equation and solve for your y. What is your y? Figure out what it is. Then you plug in both. Okay? So let's move on to problem number 4. Is everybody good with problem 3? Okay. Problem 4. We want to find the equation of the tangent line for that curve at the point -2, 1. So I want you guys to start it out. D dx of, hey, this is a lot easier, just x plus 3y squared equals 1. Find the derivative. What is dy dx? All right, ladies and gentlemen, looking at the time, let's go ahead and finish this one up real quick. And then I'll just have a thing to talk about on the last one. We won't have time for it, but that's okay. All right. What is the derivative of x? 1. What's the derivative of 3y squared? Times. Anytime we take the derivative of y, we have a dy dx. Equals? Okay, what do I need to do to isolate my dy dx? All right, so 6y dy dx equals -1. And then? And so our dy dx is just -1 over 6y. That's our derivative, right? Okay, we're not done though. We want the equation of the tangent line. So our form y minus y1 equals m times x minus x1. What do we need to do an tangent line equation? What do we need? It's two things. What do we need? Point and a slope. Are we given the point? Yeah, it's right here. Even it's labeled point, right? There's our x1, y1. Great. We also need slope. How do we find the tangent line slope? What do we use? The derivative. Did we just find the derivative? Yes. So that is dy dx at the point -2, 1. Now, when we look at this equation, though, and I heard a group talk about it, do we have a place to plug in x? In our derivative equation right here that I'm pointing at, is there a place for x? No. So what is the only value I need to plug in? So that is negative 1 over 6 times 1, just the y value. So what's our slope? 1/6. Equation, what would it be? Y minus 1 equals negative 1/6 times plus 2 or minus a negative 2, right? That would be your equation. You would stop there and be done.